Okay, guys, welcome back. I'm glad to have you back here for the first recording in the second semester. We are going to discuss the unit will be atomic theory and atomic structures and periodicity. You will be able to describe the wave properties and characteristic speed of propagation of radiant energy. You will be able to use the relationship lambda nu equals c, which relates the wavelength and frequency of radiant energy to its speed. You should be able to explain the origin of the expression line spectra. Your homework, remember the homework, you do it tonight. You do not wait for any extension that I put on the electronic homework. The only reason why I put that extension is if you have problem with the computer tonight, or if you don't have electricity, or if you are not here. If you are here, okay, you came to school, you need to do the quest tonight. You should never wait for that extension. Okay, you need to do quest quantum concept 8A. And I'm sure all of you already joined the new group for the second semester because I'm going to archive the first semester. You will not have access to it. So make sure you do it today. Now, why study electronic structure of atoms? Why should we care? Chemical behavior of atoms is almost entirely determined by the number and arrangement of the electrons. Okay? And then an understanding of the energy of the electrons and how they interact allows a chemist to explain many chemical and physical properties. Now, to understand the electronic structures of the atoms, let's just open a parenthesis right now. We need to discuss light. Okay? So let's talk about waves. What are waves? Waves are periodic variation of some quantity. Okay, so it depends what you are talking about. If you're talking about water wave is the periodic variation of the height of the water. If you are talking about sound, okay, sound wave will be a periodic variation of the density of air, of the medium. Talking about light would be a periodic variation of an electronic media. So, we need also to review the anatomy of a wave. I know you studied this in middle school. Let's just quickly review the different parts of a wave. So if you have a wave, okay, so you have the wave like that peak, okay, that's what we call a crest, okay, and then that lowest point is the trough. What is wavelength? Wavelength is the distance between one peak to the successive peak, or it would be the distance between one trough and the successive trough. Or in other words, wavelength is the distance between two maxima, or wavelength is the distance between two minima. What is amplitude? If you have the midpoint right here, the amplitude is the height from that midpoint to the crest, or it can be the difference between that midpoint to the trough. So this would be negative, this will be positive, amplitude. And what is frequency? Frequency is the number of cycle per second. Number of cycle per second. What unit will we be using? We will be using a meter, or mainly nanometer, for wavelength. So you should be able to convert meter to nanometer. Okay, 1 meter equal 1 times 10 to the 9 nanometer, because they will usually give you the wavelength in nanometer, and the speed of light will be in will have meter in it. You should always remember to make that conversion. What is the speed of light? Okay, the speed of light, that's meant for any light. It's not just visible light. In a vacuum, we use the symbol C. Speed of light equal wavelength time nu. Nu is a Greek letter. It is a funny V. Okay, so you have to be very careful when you look at that V to know if it's nu for frequency or a normal V for velocity. So you have to be careful. So let me repeat. C, that means speed of light, equal wavelength, that is the symbol Greek letter lambda, time nu, that is frequency. So speed of light is a constant for any kind of light. That constant is 3 times 10 to the 8 meter per second. So you can store it on your calculator. How about if you call it C? Okay, alpha, and then press C, and then put 3 times 10 to the 8 meter per second, because you will be using it a lot. Okay, so based on that formula, you can see, because C is a constant, if you have long wavelength, that means it has short frequency. If it has a high frequency, then you have short wavelength. Sometimes we think that all lights are visible light, when visible light is only a very small portion of the whole electromagnetic spectrum. Okay, the visible light is just a very, very small portion. You need to know the different kind of lights in order by wavelength. So the kind of light with the longest wavelength is radio wave. After radio wave, we have microwave. After microwave, we have infrared. After infrared, we have visible light. Visible light, we have UV, ultraviolet. After ultraviolet, we have X-rays. And after X-rays, we have gamma rays. So you need to know those lights in order of frequency or in order of wavelength. Remember, if it's not a mistake, I will answer the questions after the recording. Remember, the longer the wavelength, the shorter is the frequency. That means radio wave will have the longest wavelength, that means the smallest frequency. And gamma rays would have the smallest wavelength, that means the highest frequency. And frequency and wavelength are inversely related. Frequency and energy, they are directly related. You also need to know the different colors of the visible light in order by wavelength. So remember, on this side, if you have infrared, that's mean in the visible light, the red light will be on this side. If on this side you have UV, on this side of the visible light, you have UV, that means the violet will be on this side of the visible light. So from middle school, you learn Roy, G, Bev. Okay, so you have your red, you have your orange, you have your yellow, you have your green, you have your blue, you have your indigo, and you have your violet. So you need to know those colors in order. One unit we did not talk about. The unit for frequency is, we said frequency is number of cycles per second. But for the unit, we only use per second. We don't use the cycle. The unit for frequency is per second, or the unit is hertz. Okay, per second or hertz, or the unit for frequency. The unit for wavelength is nanometer. The unit for C is meter per second. So why don't you pull out your calculator right now? Let's just go ahead and solve the first problem. A brilliant red colors seen in fireworks are due to the emission. Now let's think a little bit. When they say emission, that means it's releasing heat. Emission is going from a higher energy level to a lower energy level. Absorption is positive, is going to a higher energy level. To light with wavelength around, they give you the wavelength. It's 650 nanometer. When strontium salts, such as strontium nitrate and strontium carbonate, are heated, this can be easily demonstrated in the lab by dissolving one of these salts in methanol that contains a little water and igniting the mixture in an evaporating dish. Calculate the frequency. They ask me for frequency with that wavelength. Remember, they will not give you the speed of light. They will not give it to you. So you need to know it. So we said the formula C equal lambda time nu. They asked me for frequency. Therefore, frequency, which is nu, equal speed of light, which is C over lambda. Therefore, frequency equal speed of light, which is 3 times 10 to the 8 meters per second, over our lambda, which is 650 nanometer. But because I have meter in my speed of light, I need to write the wavelength in meter. So I will write 650 times 10 to the negative 9 meter. I know this is not the right way to write scientific notation, but since just to do the math, let's just leave it like that. So meter and meter will cancel out. So 3 times 10 to the 8 divided by 650 times 10 to the negative 9. The answer is, thank you very much, 4.6 times 10 to the 14. What is the unit? It is hertz. Yes, it is hertz or per second. Hertz or per second. Remember always to convert your unit in meter. Now, there was a guy. That guy was doing his submitting his dissertation for his doctorate. It is Max Planck. He sent the dissertation, and then the people checking the dissertation, they were so confused of what he wrote. They were so confused, they sent it to Einstein because they thought maybe he did something wrong. He was not going to get his doctorate. They sent it. When Einstein read that dissertation, he was so surprised. He sent a letter back, a note back to those people, to those professors, to tell them that Max Planck, he said something that shows exactly that he's brilliant. And 5 years later, he got a Nobel Prize just because of that dissertation. And he was the very first person, or the only person, who got a Nobel Prize based on a dissertation for a doctorate. What did he say? He showed that light can behave as wave. Light can also behave as a particle. That's what we call a dual. Okay? Wave particle duality of light. And someone later, and I will show you later, someone else, okay, Louis de Broglie, he's French, and if you hear any YouTube, they will pronounce it as de Broglie. They will give you all kind of pronunciation. But it is French, and I do speak French. So it is Louis de Broglie. Okay, even in the name Z site, the lady will tell you de Broglie is wrong. It is de Broglie. It is de Broglie. So I will show you later that he said that matter can also behave as wave and as particle. Okay, so let me repeat. Light, it depends on the experiment you are checking. Light can behave as wave and particle. It depends on the experiment and who you talk to. Matter can behave as wave and particle. So let's use different formulas to show how they can behave different ways. So Planck shows that energy can be emitted or absorbed in chunk, okay, in specific amount. It's like you go to a soda machine. If a soda is 50 cents, it doesn't matter if you put 45 or if you put $1.05. The soda will be released only by a chunk of 50 cents. By 50 cents, every 50 cents you will get one can. So it's like the light can be emitted or absorbed in chunk, in packet, okay, of light. That's what we call, of energy, that's what we call a quantum. A quantum of energy is a packet of energy, and the formula for that energy is Planck constant time frequency. You need that formula. You will be using it to solve problem. Energy equal Planck constant time frequency. And if that quantum of energy, that packet of energy, is a packet of light, we call it a photon. A photon is a packet of light, and then the one photon will emit energy, one Planck constant time frequency. That n will be the number of particles. That n, the number of particles. What is the so energy is quantized. Energy is quantized, okay, in packet, in chunk. So what is that Planck constant? I would advise you to also enter it on your calculator. The symbol is H. Don't ask me why. Planck constant is H, and that number is 6.626 times 10 to the negative 34. It is joules second. So when you multiply it by frequency, which is per second, so the energy will be in joule. They will give you that constant on your formula packet, but if you enter it on your calculator, you will avoid a lot of mistake. Okay, so it doesn't matter what frequency you use, that frequency and that constant will give you that photon. 6.626 times 10 to the negative 34. Energy comes in small quantities, we said, called quantum. So light travels as a packet, as a particle, and as a wave. A particle of light is called a photon. A photon. So why don't you get your calculator and let's solve our second problem here. Okay, a blue light in fireworks is often achieved by heating copper 1 chloride to about 1200 degrees Celsius. Then the compound emits blue light having a wavelength. We have wavelength here. What is the increment of energy? They ask me for energy, the quantum that is emitted by that wavelength. The only thing they give me is wavelength. They ask me for energy. So energy equal Planck constant time frequency. Therefore, energy equal, I should know my Planck constant, which is 6.626 times 10 to the negative 34 joule second times, I don't have frequency, but I know frequency equal speed of light over lambda. Therefore, time speed of light, which is 3 times 10 to the 8 meter, 3 times 10 to the 8 meter per second over my lambda. My lambda is 3. Why don't I put it in meter? That's mean 450 nanometer times 10 to the negative 9 meter. So the meter will cancel out. Per second cancel out. my answer should be in joule. And the answer is, okay, 4.42 times 10 to the negative 19. Thank you. Negative 19 joule. All right, let's move on. Now, this is very important. Listen carefully. Now, there were three guys who did some experiment, and they realized every time light is emitted, light is not, when you see light, it's not always a spectrum. That's mean blended colors. Sometimes you see line spectrum, line, specific line for specific elements. You will see the specific lines. So those guys, they check whenever the electrons, important, listen carefully, when the electrons fall all the way to the first energy level, okay, you cannot see that light. It is in the UV range. When the electron is emitted, okay, so a electron absorb energy and go to a higher energy level. When it's coming back down, if it's go all the way to the first energy level, our eyes cannot perceive it. Okay, it is in the UV range. So this series is called the Lyman series. Remember that when it falls all the way down to the first level, it is the Lyman series. Okay, those are different people. Now, when it falls to the second level, those energy move to the second level. That's when we can see it. It is in the visible range. This we call it the Balmer series. Okay, Lyman series, UV. Balmer series, visible, we can see it. When those electrons fall to the third level, they stay right here. Okay, we cannot see it. It is in the range of infrared. It has a longer wavelength. That's what we call the Paschen series. If you check books, you will see more series. More. You don't have to worry about them. Just remember, the Lyman series down to the first level is in the UV range. The Balmer series, the second level, is in the visible range. Paschen series, third level, is in the infrared. And those are line spectrum. It is not just blended colors. It's that white light where you see a nice rainbow of colors. You have specific line. It's like a fingerprint for that atom that will emit specific lines. Okay, we are almost done. Let's do one more formula. We will solve one more problem. Now, remember I told you about this is another guy. Okay, it is a Rydberg. So you may hear Rydberg different ways. Rydberg. This is another formula you need to know. This is a formula to measure the amount of energy that will be emitted, the change in energy when those electrons move from a specific level to another specific level. Okay, if the electrons fall from the fourth level to the second level, what is the change in energy? From any level, what is the change? This is the formula you will be using. Change in energy. You will see different ways in your formula packet, but I would advise you to use it the way I'm going to tell you right now. Okay, change in energy equal. I'm going to change that sign in a minute. Okay, it's up to you. Negative 2.18 times 10 to the negative 18 joule. That's what we call the Rydberg constant. Rydberg constant. Times 1 over the final energy level squared minus 1 over the initial energy level squared. I like to use it better this way, so I won't have to deal with negative. Okay, delta E equal, why don't you make that constant positive? Okay, 2.178 times 10 to the negative 18, and then switch those. 1 over n initial squared minus 1 over n final squared. It's up to you. It will give you the same thing. If you put the Rydberg constant at positive, just put the initial minus the final. Alright? Or if you want to go the long way, then you would do it for initial first and then do it for final second and then subtract them. Okay, I like this way better. I do the change at once. I don't have to do it splitting the final and the initial energy and then subtract them. The Rydberg constant. So let's solve a problem using that formula. Calculate the energy required to excite. Remember, excite, go to a lower energy level. This is our last example. Lower energy level to a higher energy level. Let me tell you, energy is not negative. Okay, listen carefully. Energy is not negative, right? But you will find negative. The negative just means the energy is released. Okay? When it's positive, it is absorbed. If you were to use that energy in a second step in a problem, make sure you use it as a positive number. Okay? So there is no negative energy. Calculate the energy required to excite the hydrogen atom from level 1 to level 2. Also calculate the wavelength. They asked me also for wavelength of light that must be absorbed by a hydrogen atom in its ground state to reach this excited state. So we have to answer 2 questions here and I will be done. They ask for energy. So delta E equal, now this is the Rydberg constant. I'm going to use a positive number. Okay, 2.1789 times 10 to the negative 18 times, because I put positive, I will put 1 initial first. You say from, because from, this is my initial, 1 squared, minus 2 is my final, is 1 over 2 squared. Okay, equal. So this is the energy. Let's see who can do this problem. Who can solve this? I have it right here. The answer is yes. 1.63 times 10 to the negative 18. Thank you. Joules. It is energy, it is joule. But they asked me for wavelength also. They asked me for wavelength. What formula do I use? Okay, E equal H nu. Therefore, E equal my H, which is the Planck constant. It is 6.626 times 10 to the negative 34 meter joule second. And then my V, my nu, is the speed of light, which is 3 times 10 to the 8 meter per second divided by the wavelength. But that's what I'm solving for. Is that right? Divide by wavelength. Okay, therefore, wavelength equal my energy, which is 1.63 times 10 to the negative 18 joules divided by my Planck constant, okay, 6.626 times 10 to the negative 34. Okay, so why I do this? No, it's not true. Okay, why didn't I say write a formula from the beginning before I plug in it? Hold on. Let me reset. Okay, what did I write the formula for? This is my energy. Energy equal Planck constant times frequency. Therefore, I'm solving for, okay, let me write energy equal Planck constant times C over lambda. Okay, I'm solving for lambda. Therefore, lambda equal Planck constant times C over E. Right? Therefore, lambda equal 6.626 times 10 to the negative 34 times my speed of light, which is 3 times 10 to the 8 meter per second divided by my E. What was my E? 1.63 times 10 to the negative 18. Negative 18. So what is my wavelength? One 1.217 times 10 to the negative times 10 to the negative 7. This would be meter. It is meter.